Hey everybody, your Friendly Math Tutor here with another lecture video. Today we move on to Unit 7 on differential equations. So make sure to like, subscribe to our channel, check out TikTok, Facebook, Instagram. Also check out our Patreon where we'll have even more videos and worksheets. And let's dive into today's lesson. So like I said, we've got the last couple of units, we've done multiple parts. Today we're going to do the whole unit here. And we're going to start with the idea of differential equations. So first of all, what is a differential equation? Essentially, it's just an equation, something that has an equal sign, that also has a derivative in it, or a second derivative. All right, so it's an equation that literally just has a derivative in it. That's all it is. So let's first look at the idea of verifying solutions. So we have a differential equation and we want to know, is this a solution? This is what we call a particular solution. In the next part of the lesson, we'll talk about the difference between a particular solution and a general solution. So right now we're just checking to see whether a particular solution is a solution to our differential equation. So what we do is we are first going to find the derivative. So if that is a solution, then dy dx would equal the derivative of this. So that would just be 5. And then you just substitute. So dy dx is now 5 minus y is equal to 5x plus 5, then plus 2, and that should equal 3x plus 4. So really what we want is everything to be in terms of x. So you're going to replace or substitute every y, dy dx, or second derivative, whatever the derivative is, you're going to substitute that in from your particular solution, and you're going to see, does the left side equal the right side? I think we can already see that it's not going to work, but let's just look at this. So it's 5 minus 5x minus 5 plus 2 equals 3x plus 4. The 5's cancel, you're left with negative 5x plus 2. That definitely does not equal 3x plus 4. So the answer is no, this is not a solution. The point of the second problem is for 2 reasons. You could have a second derivative and then just the notation. So one notation you'll see is the dy dx notation, and the other one here we're just going to see a y prime, y double prime. So if this is a solution, I want to find y prime. The derivative of the e to the 3x is 3e to the 3x. That's just using our basic chain rule and derivative of e. And then y double prime is 9e to the 3x. If we substitute that in, the second derivative is 9e to the 3x minus 2 times the first derivative is 3e to the 3x equals 3 times y, which is 3e to the 3x. So here we got 9 minus 6 is 3e to the 3x, and on the other side we have 3e to the 3x, so the answer is yes. All right, so we can see that if we have to verify, we can just basically take derivatives and substitute. If the left side equals the right side, then the answer is yes. If the left side does not equal the right side, then the answer is no, it's not a solution. All right, it's as easy as checking solutions to like basic linear equations that you did way back in like pre-algebra. You just substitute, left side equal to right side, yes. If not, no. All right, let's move on. All right, let's move on to slope fields. So before we try to find particular solutions in like kind of like an algebraic way, we're going to look at ones that we really don't have methods to solve yet until you take a kind of a more advanced differential equations course. So the one method that we are going to learn later won't work for this. So what we do is we use slope fields, and then we are also going to learn something called Euler's method to approximate. And the way a slope field works is, imagine that you can take the integral of something. All right, that's the opposite of the derivative. And we learned about that when we took the indefinite integral. We always had this plus c, which kind of creates a family of functions, like whether I add 5 or add 10 or subtract 100. It's going to create all these different functions that are all different vertical shifts from each other. And we could have even more constants and more things happening. So what happens is we have this general solution that kind of could exist anywhere on the coordinate plane. And at each point, that general solution will have a slope, right? Because remember, derivative represents slope. And a slope field is just a visual representation of all the different slopes that we can have. And it's generally, we could obviously have a slope at like 1.5 comma 0.62, but we generally want to just get an idea of what are the slopes at each lattice point or integer value on the coordinate plane. So one thing you're going to have to be able to do is take a differential equation and sketch out a slope field, and then sketch a particular solution. So general solution, and then a particular solution given an initial value. We'll talk a lot more about that going forward. So here I just want to demonstrate, well, how do you do this? So all you do is each one of these points that are highlighted, there's 12 here. In reality, there's an infinite number of points. I'm just going to go over how to do these 12. Each point has a coordinate pair. So if we look at this point here, the coordinate pair is -1, 0. That's going to lead to a particular slope of some general solution, which is kind of like the integral of this. But we can't just integrate this, it's too complicated. So what we do is we simply just plug in the point. If I plug in -1 here, I get -2 minus 0, so I get -2. So whatever the general solution is, whatever our original function is, that such that we take the derivative that gives us this, is going to have a slope of -2. So I'm going to show that by making a slope like this. That's a negative slope, and it's a little bit steeper than 1, so we'll just do the best we can. Let's pretend that that now means -2. Everything else will be relative to that. Then I go across and I plug in 0, 0. Well, if I plug in 0, 0, I get 0. Oops. So I get a slope of 0. Well, a slope of 0 is a horizontal line. So I'm going to have a horizontal line here. I realize now I probably should have used different colors, but I'm just going to keep going with the blue. So then I plug in 1, 0. So what's going to happen is when I'm plugging in 0 for y, you can start to take shortcuts, then this is just going to be gone. So now I'm going to I'm only plugging in 1 for x, and I'm going to get 2. So I need it to be a pretty steep slope. And then I'm going to plug in 2 for x, because again, y is 0. I'm going to get 4. So I need an even steeper slope. All right, so again, you're just doing the best you can. This is supposed to be steeper than this. I didn't want it to be vertical. So now that's it. So now let's go across. Let's do it this way. Let's pretend y is always 1. Well, if y is 1 and x is -1, I'm going to get -2 minus 1 is -3. So it's going to be a little bit steeper than this, but still negative. And then I'm going to plug in 0, 1, so that's going to give me -1. So I get a slope of -1. Let's say that's that. Then I'm going to plug in 1, 1. So that's 2 minus 1 is 1. So I'm going to get a slope of +1. And then I'm going to plug in 2, 1. So that's 4 minus 1 is 3. So I get an even steeper slope of +3. But not quite as steep as this. Again, I'm not doing this is very difficult to do perfectly. When people degrade this, they're just going to be looking for, is it positive, is it negative, and are they making it steeper than 1 or less steep than 1? All right, let's keep going. -1, 2 is going to be -2 minus 2 is -4, so it's negative and very steep. 0, 2, we're going to get -2, so it's kind of steep, but still negative. 1, 2, we're going to get 2 minus 2 is 0. So a nice horizontal line. That one's easy. That's one they're going to look for to make sure they're correct. And 2, 2 is 4 minus 2 is 2. So it's +2. So let's say that's something like that. All right. So that's just an example of a slope field. If you think I could have done better with some of those, that's fine. Just do the best you can, representing a numerical slope for each coordinate pair. That's the key thing. Now what happens is this thing kind of goes on forever, and it represents the slopes of all of our particular solutions, because we got all these different particular solutions, because when we integrate, we're going to have these constants that could be any number. So it's going to create a whole family of functions. we want to sketch a solution for which y of 0 equals 1. So that means this is like the coordinate pair 0, 1, input 0, output 1, which is here. So we have to just kind of figure out, well, what would a solution look like that went through here? Well, if I kind of follow it this way, the slope is pointing this way, and then it's going to be even more. So it's going to kind of be like this. And then if I keep following this slope, what's going to happen is this slope is just going to guide it back up this way. And then if I go this way, this slope's going to kind of push it this way, and then like that. Again, we are just estimating, but what you're going to do is you're going to kind of like sketch a solution that definitely goes through that point, and then it kind of follows the slopes that are already there. You get those slopes are kind of guiding it, right? Something down here might go like this, then go this way, and then go back up that way. If we had slopes that were pointing it down, it would then go this way. So we're just kind of following the slopes. Again, there's not like one particular answer. You could be looking at this and be thinking like, oh, I would have done this. Again, as long as it generally follows the slopes, someone grading this would have to think like, okay, that works. All right, it's usually like, if you're doing a slope field, sketching it, it's obviously a free response question. If someone grading it, it's usually that particular solution is worth 1 point. And if they look at it and say, oh yeah, they followed the slopes. If you go like this, and then from here, I just like turn this way, so it's not even a function, or I just go against the grain, then they're going to say, okay, they don't get a point here. All right, so I hope that makes sense. We're looking at some things that are kind of subjective here when we're drawing the slope fields and sketching the solution, but hopefully now that makes sense as to what a slope field is, individual slopes at each lattice point, and then sketching a general solution through a particular point. I change a particular point, it changes what the general solution looks like because I'm following different slopes. All right. Okay, let us move on. All right, let's move on to our next method of approximation called Euler's method. So Euler's method is going to be similar to linear approximation or local linearity. And what we're going to do is we are eventually going to approximate some value using only the differential equation, not actually finding the original, given some starting value, and then we're going to build our way to some other value. So let's review. Let's look at the idea that, let's say we know this value here and we're trying to approximate this value. Let's imagine that there is some tangent line here. And the equation of a line is y minus y1 equals m times x minus x1. And let's say that this has the coordinates x0, y0, some initial point, and we're trying to find these coordinates x1, y1. Well, if we were to use this, this formula, things are going to switch up a little bit. We're actually going to be using this point. So this is going to become, let me just double check something. Yeah. This is going to become y minus, y1 is really y0 or y naught, and m is the slope of this. So it's going to be f prime of whatever our point is, which is x naught, y naught, times x minus x naught. And what happens is, this is now going to end up giving us, like if we think about this, if we want to approximate this point, this equation, if we plug in x1, is going to approximate, if we plug in x1 to this line, it's going to approximate y1, all right? So what we end up getting is y1 is approximately equal to, I'll add over the y naught, plus f prime of x naught, y naught, times this is x1 minus x naught. So this is a way to approximate this, but it might not be the best approximation. So let's say that instead of that, I'm going to change this. I'm going to make x1 go here. So now that is much closer to the actual curve. And then what I'm going to do is I'm going to make an equation of a tangent line that goes through this point now. And my x2 is now much closer than my x1 was. So what this is called is the distance between here, this value, is what we call the step size. We're going to call that delta x. And you're always going to use equal steps throughout. So the whole point of going over this was just for you to see that we're using the idea of the equation of a tangent line and this idea of linear approximation. And instead of, if we want to approximate something that's a little bit further away, what we can do is we can just use an approximation of an approximation, and the tangent line will get us closer to where we want to be. I could do this more times, and the more times I do it, the more I'm going to be following the curve, and the closer my approximation will be. So if we had a calculator, or we want to do this on a computer, we could approximate using like 100 steps, and we would have a really, really accurate answer. But most likely you'll just have to do 2 steps, because anything after that is kind of busy work. And what this ends up being is, if I want to keep repeating the process, I just want to make sure what letters I use. Yeah. So if I want to approximate y sub n plus 1, that's based off of y sub n plus f prime of x sub n y sub n times, and what we're just going to start to call this is delta x. And this is what we call our step size. And it becomes what we call a recursive process. So we're going to do it to find x sub 1, or really y sub 1, and then we're going to do it again and again and again. We're only going to do it twice because, again, it kind of just becomes busy work. But this is our general idea that comes from point-slope formula of using, this is called Euler's method. So let's see how that works in an example. So we have this initial point here, which is, I'm going to do it like this. So this point here is -1, 2. That is a point that's on the original function. And we don't know what it is because we only have the derivative of that function. So this is our x naught, y naught. And what that's going to do is it's going to allow us to find an approximation for y1. So y1 is going to be based off of y naught, which is 2, plus f prime of x naught, y naught. That's just substituting in -1, 2 into our differential equation to get the slope, right? If you do that here, that ends up being, I believe, 4. So if we plug in -1, that's 6. 6 minus 2 is, it's 4, times our step size. So our step size is this. We're going from -1 to 0 using 2 steps. Well, -1 to 0 is 1 unit, and if we're using 2 steps to get there, each step has to be a half. So I'm going to multiply by a half. This should not change throughout the problem. So this gives me 4. All right. Okay. So now I have a new point. So what happened was I started at -1 and I took a half a step. So now I'm at -1/2. And my y value is now this 4. Now we're going to go again. We're going to find our second approximation. But this is going to be based off of y1. So when this is 2, then all of these are 1s. So y1 is, so this is x1, y1. So y1 is 4 plus, now I have to plug in this point into our derivative. So I do -1/2, that gives me a +4. Positive 1/4 times 6 is 6/4, which is 3/2. And then x squared is another +4 times 4, which is 1. So you get 3/2 minus 1, so that's +1/2. So that's our slope. And our step size is always the same. So that should be another 1/2, because I'm stepping from -1/2 up to 0, which is still a half. So this is 4 plus a 1/4, which is 17/4. So this tells me that I'm now at the point x2, y2 is if I step -1/2, a half to -1 to -1/2, I step a half, step another half, I'm now at 0. And then this became 17/4. Now I have approximated f of 0. So my answer is that f of 0 is approximately 17/4. So it took 2 steps to get there, And that's how we use the recursive process of Euler's method to solve a specific value of a differential equation without actually solving the differential equation. That's why it's still just an approximation. All right, let's move on. All right, let's move on to separation of variables. So this is an actual method, no more approximating, no more slope fields, no more Euler's method. This is an actual method to solve for, at first, a general solution, and then we are going to find a particular solution. So the way separation of variables works is we literally have to separate the variables so that we get all the y's and dy's on one side and all the x's and dx's on the other. This one I can simply just cross multiply. So I'm going to get y dy equals x minus 3 times dx. So you want all the y's with dy and all the x's with dx, because we're just going to take the integral of both sides. So again, in algebra, what you do to one side, you do to the other. We're allowed to integrate both sides, but for now, is we need, if there's a y, we need there to be a dy, and if there's an x, we need there to be a dx. So I can just take the integral of both sides. The integral of y dy is y squared over 2. And the integral of x minus 3 is x squared over 2 minus 3x. Now I need, each of these really needs a plus c, but if I add c to both sides, they could be different c's, and then I could subtract that c to the other side to give a new c. So I'm just going to put 1 plus c on this side, and typically we'll just put it on the x side. And then after that, we just want to, if we can, we want to get y by itself. So I can multiply through by 2. So this is super important. If I multiply by 2, it cancels that 2. If I multiply this by 2, that gives me 6 at negative 6x. Now, if I multiply c by 2, you're probably thinking that would be 2c. But 2c would just be a different constant. So I'm just going to also call that c. I am not violating the laws of algebra. If you do anything to the constant with another constant, like multiply by 2, you could just keep it as c. Your teacher might want you to put like C1 and then name it a different C, like C2. I'm just going to do that because this is still the same thing. And then finally, I'm going to take the square root. So I get plus or minus x squared minus 6x plus c. And that is what we would call our general solution, because I have this plus c in there. I have this constant that I could change to any number I want, creating an infinite number of graphs or curves on the coordinate plane, which is kind of related to what we were talking about before with our slope field. So that's called a general solution because it has a constant in it. All right. Now let's look at a particular solution because they give us what's called an initial value. But the start of it is the same. So I'm going to do dy, and I'm going to divide by 4y squared. And then I'm going to bring the dx to the other side, so secant squared of 2x dx. And I'm going to integrate both sides. This one I'm going to think of as y to the negative 2 over 4. And this one I'm just going to keep the same. The antiderivative of y to the negative 2 is going to be y to the negative 1 over negative 1. So it'll be like this, y to the negative 1 over negative 1, but I have a 4 there, and I'll also bring this back to the bottom. So I'm going to get negative 1 over 4y. That should be the antiderivative of that, if I did that correctly. Now, the antiderivative of secant squared is simply just tangent. The derivative of tangent is secant squared. So I get the tangent of 2x. I'm going to try to do this without having to use u substitution. I think we can kind of think our way through this. If I took the derivative of tan 2x, I'd get secant squared 2x times 2 because of the chain rule. So to offset that 2, I can just put a 1/2 in front of here. And then I'm going to have a plus c. All right, so I can multiply by negative 4. So I get 1 over y equals negative 2 tan 2x plus still c, because c times negative 4 is still just a different c that I can call c. And finally, I will flip everything. So y equals negative 1 over 2 tan 2x plus c. That's our general solution, but I want to find the particular solution. So I'm going to plug in 1 for y and pi over 8 for x. So 2 tan, that's pi over 4. If I double pi over 8 plus c, so I get 1 equals negative 1 over, well, the tan of pi over 4 is just 1, so I get 2 plus c. I can bring the 2 plus c over here, so I get 2 plus c equals negative 1. If I subtract 2, so c equals negative 3. So our particular solution is y equals negative 1 over 2 tan 2x minus 3. So we have a general solution with a c in it, and then we use our initial value to plug in and solve for c, and then plug that back in to give us our particular solution to this differential equation. All right, let's keep it going with an exponential model. So we're going to look at two applications of differential equations. One of them is the exponential model. So we got a population y grows at a rate proportional to its current value. If the population doubles every 11 years, then what is k? So we have it grows at a rate. So we can think of this, dy dt, all right? The rate at which the population y is growing over the course of time is going to be a derivative. So it's going to be dy dt. It's proportional to its current value. That looks like this. Something that's proportional is the constant of proportionality times whatever it's proportional to. So this is called a direct proportion. And that is our equation, our differential equation that we're starting at. So this population doubles every 11 years. Find k. We'll get to that. First, we want to solve this differential equation. So I'm going to have dy over y equals k dt. So k, let's remember, is not a variable. It's a constant. And then I'm going to integrate both sides. So the integral of 1 over y is the ln of y, really the ln of absolute value of y. The integral of k, well, the integral of a constant is that constant times the variable. So since it's dt, the integral of k is going to be kt, and then I'm going to have a constant plus c. Now I'm going to exponentiate, so I'm going to raise everything to the e. So e and the ln cancel out, so I'm just left with y. And this becomes e to the kt. Now, if it's plus c, that's e to the c. So that's times e to the c. Notice when I multiply like bases, I add my exponent, so I'm just breaking it up like that. And e to the c is just another constant. So I end up with y equals c e to the kt. That's our exponential model. I'm sure you've seen that before in pre-calculus. So this is kind of where it comes from. And now what we do is we've got to actually figure out the problem. So if it doubles every 11 years, so what that means is if this c here, if you think about it, if I plug in times 0, 0 times k is 0 and e to the 0 is 1, whatever this constant is really the initial population. It's what we would get if we plugged in times 0. So if the initial population is c and it doubles, it's going to double to 2c. So if I replace y with 2c equals c e to the k times 11. Now I just have to solve for k. This is pretty easy because the c's cancel out. I'm going to take the ln of both sides. So the ln of 2 is equal to the ln of e to the 11k. I can bring the 11k in front using our log properties. And then I have the ln of e, but the ln of e is just 1. So k is going to be the ln of 2 divided by 11. If this is calculator, then we could just plug that in, but let's just assume it's non-calculator, and that is the exact value. So that is a way to use the exponential model is always going to be the idea that something is proportional to, the rate is proportional to what it currently is. So it's going to start out something like this, and then we can use separation of variables and then kind of answer whatever question they're talking about by plugging in certain values. All right, let's move on to our last model. All right, last topic. This is called the logistical growth model. So we just did the population model, or is that what I called it? Population? Oh, exponential model, which is a lot of times used for population, but logistical growth model is another way for population. So the way this one works, this is what the model looks like. K is just some constant, and L is also another constant, and the P is the population. So a little bit more of a complex way that population can grow is based off of this logistical growth model. So I'll go over the things that I think are most important. We could use separation of variables. You could look that up in another video anywhere on YouTube. There's a lot of people that have great videos out there of that. I don't think that's that important for you to know necessarily. I think what's most important is obviously what I'm about to go over is all the information that we can get from the model. So these are most likely the questions that I have seen on like an AP Calc test, and the kind of understanding that you need to have based off the logistical growth model. I don't think you're going to need to do separation of variables for this. I think what I'm about to go over is, again, most likely what you'll see. So what we have is you have this thing here, this L. The key is going to be getting it into this form, and if it looks like this, if you got a 1 here minus P over L, this is what we call the carrying capacity. So what you want to imagine is you have a population, imagine some animal. You had a population of deer in some local woods. What's going to happen is those deer are going to reproduce based off of the resources that they have available, the food and anything else. And there's going to be a max amount of deer that could exist in that environment based off of, again, just limited resources. So the carrying capacity is the most amount. So basically, the deer are going to reproduce, and then as they start to use up more of their resources, they're going to have to reproduce more slowly because they won't have all the resources, and their population will kind of like level out. And that leveling out, that value that it's approaching, is what we call the carrying capacity. So what the graph of the actual population will look like is generally something like this. You're going to have this horizontal asymptote here, and you're also going to have a horizontal asymptote at 0 because you can't have a negative number of population. And you're basically going to have something that looks like this. And at this value here, so it's going to approach the L, which is the carrying capacity. And in the beginning, so the negative part doesn't make sense because this is time. That's just where the curve goes. But if we look at time, if this is time and this is the population, if you look at time 0, you're going to have some initial population. So depending on that population, if it's low, if there's a lot of resources, its population is going to increase pretty quickly. Then it's going to hit some point where its population is going to start to level out. Right here at this point is our inflection point. This is where it's going to be growing the fastest. And then it's going to continue to grow, but it's going to grow more slowly because it's going to start to use its resources that it has, and it's not going to grow as fast as it did at the very beginning. That value is always L over 2. So when it gets to half its carrying capacity, at that moment is where it's going to start to level off. So that's enough that understanding of logistical growth model, at least for AP Calc, is enough to answer the questions that they usually ask. So one of the main types of questions, which is what I want to focus on today, is they give you a differential equation. You don't have to separate variables and solve that. You can answer all your questions if you can just get it in this form. So what I'm going to do is I'm going to take dp dt, and what I want is there to be a 1 here. This is the thing you really want to do. Well, if I want a 1 there, I got to factor out a 700. So 0.0008 times 700, I think I figured that out already. It's 0.56. Hold on, I did it in the calculator. Oh, yeah, 0.56. Let me just double check that again. Yeah, 3 zeros, yeah. So 0.56p, so that's factoring out the 700, so that puts a 1 there. But then I have to do p divided by 700. To offset the fact that I took out a 700. So now I have something that's equivalent to what I started with, but looks like this. So now we can see that the carrying capacity is just 700. So one major thing is to be able to just rearrange the differential equation to get it to look like this so that you then can easily just see what the carrying capacity is. Now, the size of the population when it's growing fastest, we just talked about that. That's just L over 2. So that's going to be 350. And then the rate at which the population is growing the fastest, the actual rate, is just plugging 350 into this equation. So it would just be dp dt equals, well, what happens oh, wow, no, I actually made a mistake there. So this is, it wants the rate at which the population, oh, no, I didn't. I did not make a mistake. All right. I overthought that. So it will be. So it'll be dp dt. I thought for a second that our independent variable was t and I would need a time to plug in, but I don't, because our differential equation is only based off of p, the population, is not based off of time. So now we're back. So forget about that little setback I had in my brain. And we'll go with, we're just going to plug in p. When the population is 350, it's growing at its fastest. So the rate at which it's growing is just simply plugging in 350 into either one of these. I guess I'll plug it into the first one. And I think I did that already, and that ended up, oh no, I did not do that. So I can just plug that into the calculator now. So I'm going to plug it into the original. So it's going to be 0.0008 times 350 times 700 minus 350, which is just 350. And that gives us 98. So the rate at which is growing is 98. I didn't say what this was. Let's just say it's like deer, and the time we're talking about is year. So the rate at which its population is growing the fastest, we could say, is like 98 deer per year. All right, that would be one way we could do that. All right, so that is it for differential equations. I hope that was helpful. Again, as always, like, subscribe to our YouTube channel, like this video, and make sure to check out our TikTok, Instagram, and Facebook, where I'll be posting videos related to this topic for this week. Also over on Patreon, I'll be posting worksheets and videos going over those worksheets. And we've only got a couple more, we got to think like four or five more videos left. And we're about a month out from the test at this point. So I hope we're all studying, and I hope all this is making sense. And I will see you for next week's video.